This video is part of CAE Associates Ansys e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an Ansys channel partner since 1985 and have developed our Ansys e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of Ansys courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
Now, this particular seminar, we're going to be talking about the benefits of parametric modeling and the different tools that are available within the Workbench environment. One thing that we noted, we presented this seminar for the first time 2 days ago, and we had originally tried to meet the 30-minute limit, but we found that we went a little bit over because of the volume of material. So I'm anticipating that this seminar should take on the order of about 35 to 40 minutes, after which we will open up to a Q&A session using the chat window in the WebEx environment. So just to give you a heads up on that, if you need to leave after 30 minutes, that's fine. And you have any additional questions, you can add them to the survey and email them back to us so we can address them. So today we'll be talking about, again, benefits to the parametric modeling approach, how to set that type of modeling up in terms of defining input and output parameters, how to use the parameter set from a variety of different ways to basically do either a manual design input or to specify design points that you may be using in a subsequent DOE analysis. We're going to take a look at the parameter correlation tool today in the Workbench environment. That's a tool that enables us to evaluate the level of sensitivity of a particular parameter to the response of the system. And then we'll be using the design exploration tools to generate response surfaces from points generated from a design of experiments matrix. We will curve fit those and then use those curve fits to do goal-based or predictive optimization. And then lastly, look at a statistical approach, a Six Sigma tool within the Design Explorer environment that allows us to define a statistical distribution of our input and evaluate the output accordingly. But why would you want to model parametrically? Well, first of all, if you're using one of the commercial CAD systems out there, such as SolidWorks, SolidEdge, NX, ProE, to name a few, you're already modeling parametrically in the CAD environment. You're creating sketches that are dimensioned. They're controlled parametrically by those dimensions, and then you're performing modeling operations, things like extrusion depths and revolution angles, which are also parametric. So your model is inherently parametric on the CAD side. Why not take that geometry and that parametric nature into the analysis world as well? And you can do that with the Ansys connection products or the plug-in tools that are available with the Ansys Workbench environment. When you do this, you can gain a deeper understanding of your design at very little additional cost, because when we set up a parametric model, we have access to those parameters. We can request an update or a refresh of that geometry, and all of the settings that we've defined in our mechanical model, such as the mesh, the boundary conditions, the material properties, the output quantities, the scoping, they all get automatically remapped to that new model, because all we're doing is morphing the original model. So at very little additional cost, we can use the same model multiple times and get a very good understanding of the sensitivities of the design, and also hopefully uncover some unwanted surprises that could occur in the design process that we would want to have to find out later on down the line. For instance, look over here on the left. We're showing this red column here as a high level of sensitivity to that parameter. We want to know that up front in the process of creating our design. And we can do that with parametric analysis. We can identify a lot of these issues right up front. The basic process that we'll be using to set up the parametric model is first to identify the input parameters. These parameters can come from a variety of sources. They typically will come from the CAD model geometrically. But we can also make things like our material coefficients parametric. We may not know if say the modulus of elasticity is going to vary from lot to lot of material and may want to track that. Any loading magnitudes that we specify can be parametric. And as of version 13, we have the ability to make all mesh controls in the mechanical environment parametric. This enables us to do several things, like, for instance, doing a mesh refinement study parametrically to determine if we have a sufficient mesh to calculate or to capture the response in a particular area of the model. But it also gives us the ability to link these mesh controls to the CAD parameters. We can write associations using the parameter set between the mesh controls and the CAD parameters so that we can guarantee that we always have a consistent mesh for each design regeneration. Once we've identified our input parameters, we then move to the output parameters. These are the response quantities that we want to keep track of as we change the setup of the model. These could be things like the mass and volume of bodies. If we're doing a structural analysis, we may track deflection, stress, and strain in particular areas. Reaction forces using the probe tools, any information that comes out of the contact tool like gap and pressure, and also any user-defined results that we may specify in the mechanical environment. Now, we don't always know which parameters are the key ones in a design, so oftentimes we may want to do a parameter sensitivity study where we basically include all of the parameters that we think could potentially affect the design and evaluate their individual strengths, or what is the correlation between a change in that parameter and the response of the system. So we'll show you how to do that using one of the Design Explorer tools, and then we'll take the critical parameters that we've determined and go and do a design of experiments analysis, where we'll specify ranges that these parameters could potentially vary over, and we'll try to map the design space essentially. Once we have those individual design point solutions, we'll then curve fit them, and with those curve fits, we can then do some optimization, what we call goal-based optimization, to try to determine the optimum design configuration or the optimum set of parameter values to use for our design. We can also take a statistical approach using the Design Explorer tools. As I said, you may have a statistical distribution of your input. You can then define your input as such and try to determine the robustness of your design. What's the probability that a particular stress is going to exist for your input variables? The example that we'll be looking at today will be a component of a vice grip. We're using SolidWorks as the driving CAD system. But all of the things that I'm going to show you on the CAD side, as far as bringing those parameters across to Ansys, are consistent for all the different CAD tools. So if you're using Pro-E, NX, Solid Edge, you're essentially going to be doing the same thing when you bring those parameters across. So we're going to start with SolidWorks. We're going to take that lower jaw body, and I've made a simplified representation of it for the purpose of this demonstration. And we're going to start out by identifying some of the parameters that were used to create this CAD model and evaluating them in terms of their sensitivity. So typical ones that we're going to be looking at today would be things like the length of the lower jaw, the jaw thickness, the outer diameter of the jaw, and then a horizontal or vertical pivot distance between the two. Well, where am I going to find these parameters? I'm going to locate these on the CAD side. So let's pop up our SolidWorks model here. And our CAD parameters are found in the details of our sketches as well as in the details of the modeling operations that we perform. So just right off the bat here, if I click on my first sketch here, I have a series of dimensions that all could potentially be brought over to the analysis environment as a parameter. Now, the way that I identify particular parameters to be brought in with the geometry is to basically look at the details of that parameter and then assign to it a name that I'll be able to filter out when I sweep through that geometry and pull out parameters. So in my case, I'm using a common parameter prefix of MP, so every parameter that I would like to bring into the analysis environment is going to have that prefix. And then in addition to that, I want to rename my parameters such that they have a recognizable name. Now, the reason I do this is when I bring geometry and parameters into the analysis environment, there's no way other than trial and error for me to figure out what the relationship is between a particular parameter and the geometry. Ansys doesn't know that. Ansys relies on the CAD system to keep track of that because that's where the original features and parameters are linked together. So from a best practices standpoint, it's always a good idea to take a little time, go through your parameters, and give them realistic names, the names that I had shown on the previous page, so that when I'm doing an optimization or a design of experiments on this, I know exactly what that parameter means. I don't have to do any kind of mental gymnastics to figure out, what parameter D0 affects in terms of that geometry. So we can go through our particular sketches and our operations. One nice thing about SolidWorks is if you roll the mouse over a particular dimension, you can see the dimension name that's assigned to it. So for instance, this horizontal dimension here is D3. That's one that I won't be bringing across. Here's my jaw length. I've renamed it from its default designation to MP_jaw length, again, to filter out all parameters with an MP and to have a name that I'll recognize. Here's our jaw height over here. Here's the jaw outer diameter. We'll be bringing that across as well. And then for the additional 2 parameters, I'm going to go to my second sketch that I used to create these cutouts for the pivot points. And there's my horizontal, or what I call my pivot vertical, and my pivot horizontal. So these are the parameters that I'm going to bring across on the CAD side to the analysis environment. Additionally, in your CAD tool, you have available to you the name selection toolbar from the pull-down menu. With the name selection toolbar at the CAD level, we can define geometric entities like surfaces or edges or bodies that we want to have a name assigned to when we bring this geometry into the workbench environment. Now, these name selections can also be defined downstream, either in Design Modeler or in the mechanical tool. But if you're comfortable with the CAD side and you like to do as much work as possible in the CAD tool, you can use the name selection manager at this level, and these name selections will propagate through the process. So I've done things like created name selections for the cylindrical surfaces of the pivots, for the end of the jaw. Now, these are regions where I'm going to apply a boundary condition. So rather than having to pick the geometry in the mechanical tool, I'm going to toggle that boundary condition, in this case, to the name selection that I've defined at the CAD level, and that makes for a very robust regeneration of my individual design points. So now that I've identified my CAD parameters and I've identified name selections that I want to bring across, I'm going to open up the Ansys menu by pulling down Ansys 14 and specifying that I want to enter the workbench environment. When we do that, we're presented with the project page, and typically what you will see is just a geometry item listed on the top. But because of the number of design points that we're going to be evaluating in this webinar, I've taken the liberty of setting up the model and generating the design point solutions for you. So I dragged and dropped a static structural solution onto that geometry, and the first thing that I want to do is tell Ansys to include the parameters in the geometry transfer. I do that by picking on geometry and viewing the properties pane, which is over here on the right. And in the properties of my geometry, I click on the check mark for parameters. So include the parameters, and then additionally use the parameter key that I've specified to filter out the specific parameters that I want to bring across. We do the same thing with name selections. Click on the name selection box and specify the parameter prefix that we're using for the name selections. Keep in mind that if I leave either of these 2 rows blank, I'm going to get all of the parameters or all of the name selections that are defined in the model. Now, that can be a little cumbersome when it comes to the parameters because CAD models typically have hundreds of parameters associated with them. So you'll have this long list that you'll have to filter through to find the ones that you want to operate on. I advocate keeping your life simple, specifying the prefix for the parameters that you want, and then just simply extracting those parameters when you bring that geometry into Ansys. Now that we've done that, we can go and open up the modeling row or the mechanical environment. If you chose to use Design Modeler, you could have that in the process as well, but we've gone straight to mechanical for the purposes of this demonstration. So we've brought geometry across, we've brought parameter across, and now we want parameters across. And now we'd like to add these parameters to the parameter set inside the workbench environment. We're going to find the parameters under the details of the geometry. So if I'm using Design Modeler, I'm going to look at the details of the attach feature that was used to bring the geometry across. In the case of mechanical, I go right to the geometry itself, and I'm going to find the CAD parameters listed under the details of that particular part. Now, I've already gone through and clicked on the box to the left of these, which adds each one of these parameters to the parameter set and effectively grays out the area where the value for that particular parameter is specified. That's now controlled by the parameter set on the project page. So once I've identified those input parameters, now I'm going to go through with this initial design point, and I'm going to make sure that this is a robust simulation. So I want to make sure that I have a sufficient mesh, that my boundary conditions are working correctly, all of the normal due diligence that you would do on a standard type of analysis. So we'll start with the mesh. In the meshing tool, I went and applied a multi-zone control to this particular part because I know the multi-zone will very nicely internally decompose this part into 2 sweepable bodies. And with one single mesh control, I'll get a nice brick mesh on my part. I'm going to go and then look at my name selections. These are the name selections that we defined on the CAD side. You can see the surfaces are highlighted so we can see where they are. So these were defined at the SOLIDWORKS level and imported into mechanical for me to now use locally. I'm going to use those to define my boundary conditions. For instance, a cylindrical support that I'm going to define in the upper pivot. I'm going to scope that instead of the default geometry selection. I'm going to scope that to a name selection. And it's even smart enough to say, if you're putting on a cylindrical support, I'm only going to show you the name selections that are on a cylinder. So it even filters my list further down to the appropriate geometry selections. So I've assigned a cylindrical support to this upper pivot. I've freed up the tangential direction because I want it to spin about a pin in that hole effectively. I've then gone and defined a remote displacement. So this is going to be a displacement-based problem where I'm going to push this lower cylinder by a certain amount, again, assuming that there's some pin in the grip, and as we squeeze the grip, the pin is forcing the lower jaw upward. And then I'm going to resist that motion using a compression-only support. And in both of those cases, I've once again scoped that particular boundary condition to the name selection, so there's no picking required in this point. So again, use name selections if you choose to. It's not required. You can simply do the geometry picking, but it's always a good idea to use the name selections if you can, because when you're starting up at the CAD level, you're guaranteed to have a more robust or consistent regeneration of all of these different settings that you've specified. So we've identified a handful of input parameters that are available to us on the mechanical side. Now we need to specify some of the output parameters, and output parameters come primarily from the mechanical environment. So we're going to generate a solution here. We're going to take a look at the response to that solution. And again, do your due diligence here in terms of the way you set up a finite element model, even if it's a single design point. Take a look at the response. Take a look, animate the response. Make sure that your boundary conditions make sense. Make sure that in this particular case you have a sufficient number of elements in this high stress region to capture what's going on there. So go through, do your mesh refinement studies, get the model robust and consistent for your single design point before you kick off the parametric analysis. So I've identified a couple of results that I'd like to keep track of. The first is this equivalent stress in this fillet region here. So I go to the details of the equivalent stress, and I pick on the box to the left of, in this case, the maximum equivalent stress. So that adds that now to the parameter set inside of the workbench environment. We're going to look at the total deformation. So basically the amount of deflection at the end of the jaw. We're getting the maximum value for that. And then we can also grab things like if I want to get the reaction force, so the amount of force required to move that section of the jaw by that amount, I'm going to identify that as an output quantity as well. So I'm going to return now to my project page. There's one more input parameter that I'd like to show you, and that's the material property parameter. I may not know if my modulus of elasticity is going to be constant from material lot to material lot. If I click on the engineering data of my analysis system and open that up, you'll see that under column E, we can make any one of the coefficients that we're using for our material data parametric by simply clicking on the box in column E. That will then add that to the parameter set. So returning to our project page now, we have our parameter set that is linked to the analysis system here. Double-click on it to open it up, and let's take a look at what we have inside there. On the top, we have our input parameters. The input parameters that are coming from the static structural environment include my geometric parameters that we've already talked about, as well as the Young's modulus parameter that we just identified. Down under the output parameters, we're going to see our output quantities that we specified in the mechanical environment. Now we can make associations between these parameters by picking on one parameter and substituting its expression with an alphanumeric expression that relates to another parameter. So if I had a mesh control in this case and I wanted to make it a function of this jaw OD, I could pick that mesh control and substitute the numeric value with some alphanumeric expression, like for instance P1 divided by 10. So I'd always have 10 divisions along that dimension on the CAD side or on the mesh side. So if I need to regenerate a single design point, I can freely go in and edit the value of the input parameter here. These are all open boxes that I can change. But I may also want to look at a table of design points. So over here in the upper right-hand column, we'll see a table. We'll have our input quantities listed as the first columns, and that will be followed by the output quantities listed as well in this table. So I can freely go in now and start to add in different design points that I would like to evaluate. If I happen to have a table of these design points from some specification and it's in something like Excel form or table form, I can paste those into my design table right now and kick off a manual design study or just a regeneration of these points and tracking the output or the response of the system to changes in the input. Again, all done in the background for you automatically by virtue of the fact that this is a parametric model. So just for instance, I went in and under my jaw OD, I held it constant for a couple of points on the jaw length, and then I varied it while I held the jaw length constant. And down on the bottom here, I can create some charts and get a quick idea of what the response of the system is to changes in that input. Beyond that, there's no ability for me to do predictive response in this particular tool, the parameter set by itself. If I want to go beyond just simply tracking the response that I'm seeing, I'm going to start to use the design exploration tools, and we'll talk about those in a moment. So right now, what I'm going to do is go back to our WebEx page, and what I'd like to ask you to do is fill out a poll. How many people are actually using the parameter set and bringing parametric information across with their CAD geometry? So I've set up a poll here now, and I'm going to open it up for a minute. And if you could, just pick one of the multiple answers that we've supplied and submit your poll. And when everyone is complete, we'll reflect the results back to you, and we can get a good idea of how many people are doing this. So we're moving right along here. We're at about 32%, 45%. People are picking quickly. This is good. We have about 30 seconds left to this poll. Okay, looks like we're 73%. We're almost there, 77. All right, we got lots of participation today. That's very good. And it looks like we've topped out at about 77%. So I'm going to close the poll right now. Oh, and WebEx is telling me that people are still responding, so we've got about another 5 seconds. Okay. And now we can display the poll results. And you can see now in the window there that about 23% of the people on our call today are using the parametric capabilities. That's very encouraging. But 27% are not doing this, and we're just going to be curious as to why. So another 32% are not updating, or they're updating their design points manually. Hopefully, you've seen how easy that is to do today, and you can start to incorporate some automated design point updates. All right, so just give me one more moment here. I'm going to save the results of this poll. And I'm going to open up a second poll so that we have that ready for us when we go to the next phase. All right, let me share my desktop here again. Returning to our parameter set. Now, the way we're currently set up, or by default, when we kick off a group of solutions, or by picking on this Update All Design Points setting, with a single machine, we have to wait for these to solve in a serial fashion. So each design point gets generated, submitted to the solver, and then the parameter set waits until it receives the results from the solution. It'd be nice if we would be able to kick these off and have simultaneous solutions, if we had multiple machines that we could employ. Well, the good news is that you can do that. You can do that using what's called the Remote Solve Manager inside of Ansys. I'm going to flip back to my PowerPoint presentation for a moment here. Now, if you're not aware of this, the Remote Solve Manager is something that is a utility provided by Ansys. There's no additional cost or licensing associated with it. All it requires is that you install it and set it up, and you'll find that the installation files are all on the standard Ansys installation for that particular release. What you do with the Remote Solve Manager is you specify a bank or a cluster of machines that are available to provide finite element solutions. When a solution is submitted to the Remote Solve Manager, it finds an available machine, generates a solution, and passes the information back to the host machine. Now, what can we do with this? Well, from a parametric design standpoint, we can specify how our design updates are generated. Typically, what we like to do is generate the individual design point files on the local machine, because that's where we have the CAD system running. And it doesn't take a whole lot of time for me to pass parameters back, regenerate geometry, and regenerate mesh. I can choose to do my design point updates on each individual host machine, or each individual cluster machine. But when I do that, I have to wait for the CAD system to open on each one of those cluster machines, because these are batch processes that are being submitted. So typically what we like to do from a speed standpoint is generate the design points locally on your main machine and then submit the solutions to the Remote Solve Manager so that the individual solutions can be solved for simultaneously. And we do that by selecting on the details of the solution bar for the analysis system and indicating that the update option is to use the Remote Solve Manager. So in doing so, we generate a list of design files on our local machine. We submit it to the Remote Solve Manager. He's like a card dealer. He basically submits these solutions to the available machines, and they can be solved simultaneously. So it's a very quick and easy way, if you have multiple solve licenses, for you to generate a whole host of solutions simultaneously utilizing all of your computing resources. That being said, I'm going to return now to the workbench, or I'm sorry, to the WebEx window, and I'm going to submit to you another poll. We're curious now how many people are utilizing the Remote Solve Manager, or how many people are aware that they had it at their disposal. So I'm going to ask you now to just pick one from one of the available answers there. Okay, moving right along here, we're at about 82% participation. And it looks like we've topped off at about 82% here. So I'm going to, once again, attempt to close this poll. And it's going to take about another 10 seconds here. Okay, and as our poll closes, I'll then echo the results back to you. And you can see that about 18% of people out there are aware of the Remote Solve Manager and using it. Another 18% didn't know that they had it. Hopefully that's some new information that you can leverage at your location. About 45% of people are not using it because it's not set up. Well, if you're having trouble setting it up, that's definitely something that we would hope to be able to help you with here at CAE. And the good news is that only actually 0% of people only have one solve license. So we've got lots of people out there that are set up to utilize this utility with multiple solve licenses. Just let us know what you need in terms of help in getting that set up and running. That will definitely help you move into the parametric analysis mindset, the ability to speed up those solutions and turn them around very quickly. So I'm just going to save the results of this poll. And set up our third poll. Okay, returning now to the demonstration. So as I mentioned when we last looked at the parameter set, once we've generated these design points, we really are not able to do much more in the parameter set itself than sort of track the response and get an idea of what some of the sensitivity is. What we'd like to do now is sort of automate this process and be able to, number one, identify critical parameters, and number two, start to do some predictive analysis. So we're going to switch back now to the project page. And what we'd like to do is begin by identifying which parameters we think are critical to the design. Now we can use the Parameter Correlations tool down here under the Design Explorer menu in the lower right-hand corner of the screen. We drag and we drop that onto the page, and then we double-click on it to open it up. Now the Parameter Correlation tool will basically generate for us a set of design points, generate the solution, and then supply back to us a measure of the degree of strength of the change in the input versus the response of our system. So the first thing that we do is identify the details of our parameter correlation, the type of correlation that we're going to use. We have a choice essentially between a linear and a nonlinear type of correlation. We can tell it if we have existing samples in the parameter set to reuse those. We can preserve these design points so we can keep the solutions and use them later in the design of experiments step of the process. But additionally, we'd like to say, all right, let's start out with, say, 100 samples. Now, the more samples you use, obviously, the more accurate your correlation is going to be. But even if I say 100 samples, it's not necessarily going to have to generate that because it's going to do some checking when I enable the auto stop. It's going to look at the standard deviation, and based on a convergence criteria on that standard deviation, is going to determine if it needs to continue to vary that particular parameter or if it can eliminate design points from that list. That's illustrated here. I requested 100 samples, and I received back a sample size of 60. So It was able to determine that a lot of the variation that I was asking for was not required. So that's the setup of my parameters correlation. Next, I go to the individual parameters themselves, and I specify the range, the upper and lower bound that this parameter could potentially see. Now, this is actually a very important part of setting up a robust parametric model, because you're not necessarily guaranteed that a particular design point that you've specified with a particular parametric value is going to regenerate on the CAD side. One thing that you can do is go back to the CAD tool, and you can evaluate your upper or lower bounds of your parameters to make sure that they regenerate. But if you want to automate that process to a degree, you can simply set up the correlation tool, set up your expected ranges, and kick off an evaluation of the correlation points. What the Workbench environment will do is sweep through the correlation points, and if it finds one that does not regenerate, it'll give you a regeneration error for that point and move on to the next one. So if you want to kick off this solution, walk away, come back, you'll see which of those points you were not able to regenerate, and you can go back, figure out why that's not occurring on the CAD side, or adjust your parameter ranges accordingly. So it's a quick and easy way to determine whether or not you're going to get all of your design point solutions before you go into the design of experiments aspect of the problem. Now, the results of the correlation matrix, as I mentioned, are essentially the relationship between a change in the input versus changes in the output of the system. So what we see here are the input variables followed by the output variables on the first column and the first row. Now, up in the upper left-hand corner here, we have a mapping of the input parameters to themselves, and we see we have a very strong correlation, as we would expect on the diagonal. That's basically mapping each parameter onto itself. So anything that we see with a dark red or a dark blue is going to be a strong correlation between these parameters. Anything that gets closer to gray is going to be a weak or zero correlation. Now, in this case, I have zero correlation across my input parameters because I've assigned no relationship between them in the process, so I would expect that. Where my results become interesting to me, though, are when either in the upper right or the lower left-hand corner, where I have a comparison of the input to output response. So let's take a look at the first column here for parameter number 1, and take a look at the output response down at the bottom of the column. We can see that we have a very strong correlation between a change in the jaw OD, parameter 1, and the reaction force that's required. So that's a parameter that we want to hang on to in our DOE. Moving over to parameter 2, we have a fairly moderate correlation between the equivalent stress, the total deformation, and the jaw length. Moving over to parameter 3, it looks like we have a very weak correlation. When I indicate weak, it's close to 0. I can look at my little histogram up, or my contour menu up on the top here, and anything that is not a dark color represents a weak correlation between the input and the output. Parameter 4, pretty strong correlation to the equivalent stress on the top of the jaw. Parameter 5, weak correlation again, not much going on there. And then parameter 11, in this case, my Young's modulus, there seems to be a moderate correlation between the Young's modulus and the equivalent stress. So that's one that we're going to keep. So I think just by looking at this, we can eliminate from our DOE parameters 3 and parameters 5 just based on their weak correlation to the response. We can further evaluate that or confirm that looking at the global sensitivities of these parameters. And if we go from output quantity to output quantity, displayed across the bottom here, we can see that there is virtually no response for parameter 3 for the various outputs. So that one we're going to eliminate right off the bat. Looking at parameter 5, it has the weakest response of all the different parameters, with the exception of parameter 3. But the remaining ones, parameter 1, parameter 2, 4, and then P11, the Young's modulus, have a fairly strong coupled response with the output. So those are parameters that we're going to hang on to. Other things that we can look at, the determination histogram and the determination matrix are measures of the predictive quality of these parameters and their design points. So looking at the histogram, we basically see the strength, the predictive quality here, and we can see that parameter 3, if I go through these, parameter 3 doesn't even show up on the list. So that's one that we're definitely going to eliminate. Parameter 5, again, being fairly weak. We're going to keep the remaining 4 parameters here. The determination matrix looks a lot like the correlation matrix, again, showing predictive quality. So we're pretty confident here that parameters 3 and parameters 5 are really doing nothing in terms of our predictive capability. We can eliminate them from any subsequent optimization or design of experiments analyses. So we've identified our critical parameters now, and now we can go and utilize that list to try to do some predictive work. 2 different ways we can do this. One is to use the goal-based optimization tool. We grab that from the list, drag it onto the project page, and open up the design of experiments page. Under the Design of Experiments page, we have a couple of different ways that we can set up our DOE matrix. We can use one of the default models like the central composite design, or if you happen to have your design point solutions already generated, either in the parameter set or if they came from the correlation study, you can import those directly, so there's no need to resolve those particular design points. And that would be a custom or a custom DOE plus some sampling. You can add additional sampling points to improve the quality of your curve fit. We go next to our input quantities, and we eliminate the input parameters that we saw had weak correlation. And then we go in and we specify the lower and upper bounds of our parameters, and then a type of parameter that this is going to be defined as. It could be a continuous, so it's going to be a upper-lower bound within that range, or it could be something like a discrete parameter, where this particular parameter can only take discrete number values in that process. So it all depends on how that parameter affects the overall design. We do the same thing where if we're using the remote solve manager, we kick off all these design points. Now, the reason we're doing that correlation, as I mentioned before, is the number of design points required in a DOE is directly dependent on the number of input parameters. So if you eliminate input parameters, you eliminate required design points. So that correlation step becomes a nice time saver for you in that regard. So we go back to our parameters that we're interested in. We specify their ranges. We generate the design point solutions. Having done that, we can return and now look at the response surface, or basically map the response of these input or the output parameters to changes in the input. So we can look at 2D or 3D responses where we can map in a 3D case, we can map the response of change in 2 input variables to 1 output variable. You can set up multiple response plots. You now have polynomials that relate the response to changes in the input. With those polynomials, we can now do something called a goal-based optimization, where we come into our parameter list and we specify goals, and we'd like to find the best fit to that curve for our particular goals. So I typically start out with the output quantities. In this case, I've taken my 2 stress quantities and indicated that I would like to target a value that's less than or equal to a particular value, in this case 9,000 psi. When it comes to the reaction force and the total deformation, I'd like to minimize both those quantities, because this is a vice grip after all. I'd like to require a minimum amount of force to be able to generate as much clamping pressure as possible. So I want to minimize the deformation as well, because that represents slop in the system, which would make my vice grip less valuable to me. So I'm going to specify that I'm minimizing both those quantities and that I have a higher level of importance on those particular parameters. Moving over to our input quantities on the left here, the Young's modulus I really have no control over, so I leave that as no objective. The same with the vertical pivot. I found that had a relatively weak correlation, so we're not going to assign an objective to that quantity. But in the case of the jaw OD and the jaw length, I'd like to make the vice grip as small as possible, because that minimizes the amount of material required and the weight of the tool. So I'm going to try to minimize those as a goal. So I set up my goals. I then generate candidate design points, or curve fits, and I can look at the response of those candidate design points. And again, these are values of the output that are evaluated from the curve fit. If I find a particular design point that I'm interested in, I can then verify it, or effectively send these input parameters back to the mechanical environment and get a deterministic response that I can compare to my curve fit. So the row on the bottom here, the verification row, is an actual finite element solution output, and I can compare that to the curve fit value to evaluate the goodness of fit in my response. If I find that there's a substantial or notable difference between these quantities, I want to go back to the response surface and change the way that I'm developing it, tighten up the accuracy to increase that goodness of fit. And those are all topics that we would discuss in more detail in a full design of experiments class. One last thing to show you here. If we wanted to take a Six Sigma approach to the analysis, we could drag and drop that from the toolbar onto our project page. We open up the Design of Experiments tool. We're going to have a different set of design point variations here, because now we're assigning to the input quantities a distribution that is statistical in nature. So, for instance, if I happen to have some information on my Young's modulus that represents something like a normal distribution or a bell curve, I can assign the input or the probability based on the mean and the standard deviation to give me a distribution of that sort for my Young's modulus. In the case of something like a dimensional value, you may only know the min and the max value for that dimension. So you may use something like a uniform distribution. Or if you had some additional information like a common point, you could use a triangular distribution. So there's a whole number of different distributions that you can use that are valid for different types of analyses or different types of data that you have, and it all comes down to how much information you have about that particular parameter going into the analysis. So we set up that probability distribution of our input. We kick off the solution of our design points. We can go and generate our response surfaces. We do that in the same way that we did for the goal-driven optimization. But in this case, what's of most interest to us is the basic robustness of the design, or the Six Sigma result. So now we can go and we can look at the probability distribution of these output quantities. So the particular stress, the probability, and then the sigma level associated with that. If I want to evaluate whether or not a particular design is of Six Sigma quality, Six Sigma quality being that only 3.4 in 1 million parts, we'll see, say in this case, a stress of that amount or greater. I can simply go in, change this from percentile to quantile, and indicate that I'd like to put in a quality value of 6 sigma, or 0.9999966. That would be 1 in 3.4 million parts. That reflects back to me a stress of 11,492 psi and a sigma level of 4.5. The Six Sigma approach takes into account a 1.5 sigma drift. So this 4.5 sigma with that 1.5 drift would give me a 6 sigma stress. What that says is that 3.4 in 1 million parts may see a stress of 11,492 psi or better. If that 11,492 psi stress meets my stress criteria, then I can be confident that I have a robust or a 6 sigma level of quality in my design. Okay, I'm going to return back to our polling page again, and I'm going to ask you to answer one more poll before we conclude the webinar here, and that is essentially, are you using Design Explorer, and do you have any interest in doing so? So we'll give people a chance to fill out the poll here. That's about it for my presentation material at this point. Once we've finished with the poll, I'm going to open up the chat window to questions and answers, and you see the chat window on the left-hand side of the screen. Feel free to type in a question if you have one and submit it to the presenter. And we'll try to address as many questions as we can. If you don't get a chance or you've run out of time here, because we did go a little bit over the predicted half hour, you can simply fill out any questions you may have on the survey that will be sent to you, and we will certainly make our best efforts to address that. Okay, I'm going to close the poll now, and let's take a look at the results here. Okay, so about 10% of you are currently using Design Explorer. About 24% of you do not have Design Explorer. 43% need training. Well, the good news is that CAEA can provide that to you. So please note that in the survey that you're interested in training, and we can certainly look into setting that up for you. 5% of the people out there have no time to perform this type of analysis. Well, hopefully we've shown you enough today in terms of how easy this is to use that you can start to employ this and see some benefit from it. So I'm just going to take one more moment here to save this particular poll. Give me a moment here. Okay, and thank you all for participating in our polling today.